Hello everyone. Today we're going over topic 2.2 forces and free body diagrams. Let's get started. So even though I did not mention this in the last topic, let's connect this back to kinematics. In the last unit we used variables like displacement, velocity, and acceleration. However, these variables only describe how objects move. They don't describe why objects move. In this unit we will analyze the why. We will explore the causes of motion, specifically the forces that produce motion of objects. So what is a force? Forces describe the interactions between systems that can cause changes in motion for that system. So, for example, pushing a box across a frictionless table, as shown in the illustration. As a future note, since this has an arrow, it has a direction and a magnitude, we always represent forces as vectors with a arrow on the top of it. In other words, forces cause a system to accelerate. Forces are caused by interactions between objects. An object can't exert a net force on itself. So what is net force? A net force is the vector sum of all forces acting on an object. So let's first look at an example here. If we have force 1 going to the right and force 2 going upwards, the vector sum is, remember, tail to tip vector addition. So you would go from the tail of vector F1, force 1, to the tip of vector force 2, and that's your net force. Systems accelerate in the direction of net force. Now what if we have three forces? Because you'll be analyzing multiple forces on a single object. You just add them again, tail to tip vector addition. This is the net force, and if you notice, these two forces are parallel to each other, so they cancel out. So realistically, you're only left with this vector as well. There are various types of forces in AP Physics 1. You'll deal with contact forces and field forces. Contact forces are defined by physical interactions between objects. At the microscopic scale, contact forces are caused by intermolecular electromagnetic repulsions between atoms. So if we have a box on a table here, if we zoom in at the microscopic scale, we can see how the atoms of the box and the table are actually repelled from each other. That's what causes contact forces. For field forces, they act on objects without physical contact. So an example would be gravity. This is caused by an object's presence within a field, a force field. This field induces a field force on an object. So we have gravity here. This is a whole field. These arrows represent the gravitational field, something you'll learn later. The forces that act on a system can be represented by free body diagrams. Free body diagrams, also known as FBDs, are used to represent all the forces acting on a system. So we can represent the system as a dot. The forces acting on the system start at and point away from the system or the dot in the direction of the force. So let's look at an example here. We have a box on the table again, as always. These are the forces acting on it. Do not panic if you don't know what these subscripts and what these forces mean. We'll learn them later. In fact, this one we'll learn quite shortly, but just know that when you convert into a free body diagram, the box is treated as a system. It turns into a dot, and the force vectors start and point away from that dot. What if we have multiple forces? So we add these two new forces to the object. They both occur in the same direction, so what we do is we offset the arrows a little bit to represent both. You can't merge arrows when showing the different forces on a free body diagram. Free body diagrams are used to represent all the forces, of course. They can be broken up into perpendicular components. So this practice, it's really important as it helps with deriving an equation. So, for example, we can break up the force applied. This is applied force. Someone is pulling on the object into its horizontal and vertical components, because that's what's relevant. There's only vertical components here, so we can also break it into its horizontal components, the XY axis. So we can divide it into its force applied in the X direction and force applied in the Y direction. If you have to draw a free body diagram as an answer on the AP exam, never draw components of forces into the answer. So FAX and FAY will never be drawn. If it'll often say like draw forces, not components. On the AP exam, it'll mention don't draw components, but just in case, here's a little tip. What if we slant it at an angle here? This box at an angle. Well, we still can put them into components. But for future topics, a good practice for breaking forces into components is to make one axis of a component in the direction of acceleration and one axis perpendicular to the first axis. So if we analyze the system here, we can clearly see that the object will accelerate in the direction of the incline. So we'll define it as a purple line here. So we make one axis in the direction of acceleration. So this is the one axis, and the other axis in green will be perpendicular to that one. So for any forces that are not directly on an axis, we can break them up into their components. So for the force of gravity, it's not directly on either of those two axes as mentioned before. So we divide it into its parallel direction, the purple line, parallel to acceleration, and perpendicular direction, perpendicular to acceleration. So let's go back to the forces. There are various types of contact and field forces discussed on the AP exam. You'll have the normal force, the tension force, the gravitational force, the frictional force, the spring force, and the buoyant force. We will cover each force in turn in upcoming topics. These ones have particular subtopics for them in Unit 2. The buoyant force, it's italicized because we don't see it until Unit 8. So we actually won't be dealing with this unit in Unit 2. So let's go over the normal force first. The normal force is the support force exerted on an object by a stable surface. So for a box resting on a table, we have the force of gravity, the gravitational force, and then the support force to keep it from falling down is called the normal force. The normal force always acts perpendicular to the surface the system is interacting with. The normal force is a reactive force. It is caused as a reaction due to other forces acting on an object. So it depends per situation what the force normal magnitude and direction will be. So let's say we have a force applied. If we apply it upwards in the vertical direction, we see how we don't have as much support coming from the table anymore, because if we are now applying a force in the vertical component on the block, so the force normal actually shrinks. Now, before we continue, how about we verify this acceleration vector, because I just labeled it here. Remember, the acceleration vector is always in the direction of the vector for the net force. So if we add the forces, we see how the net force is in the same direction as the acceleration vector. So let's go back to our example. If we increase the force applied, we see that now there's even less support coming from the table, so the force normal decreases. Now it can get to a point where the force applied is actually the same as the force of gravity in the vertical direction. So it's essentially like keeping it hovered slightly above a table. But when we exceed that magnitude of the force of gravity, we actually see the acceleration vector goes a little bit up. Why? Because the net force now is no longer in the horizontal direction. It's actually going vertically now. Now let's talk about the tension force. Tension is a force that pulls along any connector, such as a rope, string, or cable, when the connector is acted by an external force. So if we have a force applied here, it'll stretch on the rope, which will cause it to completely stretch out. So tension applies at every point in the connector, but these internal forces cancel out. So at every little point, there's always tension. It's always being pulled apart. But these internal forces of up and down, they cancel out. So in an ideal string, we don't consider tension in the internal parts of the rope. However, it is useful to analyze the tension force at its ends, at the rope's ends. So we have the force of gravity here on the block. We have the force of tension coming from both ends of the rope, again, trying to push the rope against the block in the ceiling. Here's a free body diagram of the situation. Now, in AP Physics 1, all strings are considered to be ideal unless otherwise stated. All ideal strings have negligible mass and don't stretch at full length, so they don't completely deform. Ideal strings have the same magnitude of tension at all points in the string. So if we analyze a part of the string here, we see how the force of tension is always equal at every point. So the direction in magnitude, the vector here is the same magnitude as all the other vectors. Now, if we have a non-ideal string, it'll have non-negligible mass or actual mass. Tension varies at different points in the string. With a vertically hanging mass like the one shown, the tension force increases at magnitude as you go up the string, because if you're at this point at the top, there's more mass hanging below you to pull on than at the bottom of the string, which is why when you try pulling on a vertically hanging rope, it'll usually break from the top because there's more force at the top, and it might reach the maximum tension force that it can support much faster than the bottom. So yeah, if we analyze 2 points, we see how the force of tension and the force of gravity pulling on it are much higher at the top than at the bottom. In systems where a string is attached to both ends, the tension force is internal to the overall system. In this system we have a 2 blocks being pulled over by an ideal pulley with a rope strapped on both ends. Internal forces do not cause system acceleration because they cancel out. So if we analyze the system components, mass 1 and mass 2, and I'm labeling the blocks, we see there's a force of gravity 1, and there's a force normal on the second block, and the force gravity on the second block. This is the full free body diagram. Or not free body diagram, but force diagram for the system. In this example, the force causing acceleration, which is the force of gravity in object 1, because these ones cancel out. So there's no vertical acceleration, or no vertical acceleration here, horizontal acceleration here, respective to the table. Tension is internal to the system and does not contribute to net force, and so we're only left with force of gravity on object 1. All pulleys in AP Physics 1 are considered ideal, unless otherwise stated. Ideal pulleys have negligible mass and rotate without friction. So that's it for the tension force, and that's it for this unit. Thank you for watching. I hope to see you next time.